There's an experiment running right now as you listen to this that has been going on for nearly 100 years. Not in some metaphorical sense, not as a thought experiment or a theoretical exercise, but an actual physical experiment sitting in an actual room at an actual university, with real materials doing real things, and nobody alive today was born when it started. It's been running through world wars, through the invention of television and the internet, through the rise and fall of entire political systems. And the thing it's measuring, the thing it's been patiently, impossibly slowly revealing, is something so fundamental about the nature of materials that it changes the way you think about what solid even means. But we'll get to that. Let's start somewhere else first, because the story of this experiment doesn't begin in a laboratory. It begins with a question that humans have been asking for thousands of years, even if they didn't know they were asking it. And that question is simply this: what is the difference between a solid and a liquid? Now, you probably feel like you already know the answer to that. And in a practical, everyday sense, you absolutely do. You pick up a rock, it's solid. You pour water from a glass, it's liquid. Easy. But here's the thing: the boundary between those two states of matter is not nearly as clean as your intuition tells you. It's actually one of the slipperiest questions in all of materials science, and the deeper you look at it, the more the line blurs, until you start to wonder whether the categories themselves are just convenient fictions we invented because our lives are too short to notice what's really happening. Think about glass for a second. The glass in your window, the glass in your phone screen, the glass in that drinking cup on your nightstand. Is it a solid? You'd say yes, of course it is. It's hard. It holds its shape. You can knock on it and it rings. But glass is strange. Really strange. When you cool molten glass, it doesn't crystallize the way most liquids do when they become solid. Water freezes into ice, and the molecules snap into a neat, repeating lattice, a crystal structure. That's what we typically think of as a solid, molecules locked into a regular, ordered arrangement. But glass doesn't do that. When you cool it, the molecules just slow down and stop moving, frozen in place in the same disordered jumble they were in when the material was liquid. There's no crystal structure, no lattice. The arrangement of atoms in glass looks almost exactly like the arrangement of atoms in a liquid. It's just that everything has stopped. So is glass a solid, or is it a liquid that forgot to finish becoming a solid? That question has genuinely haunted physicists and materials scientists for over a century. There's an old myth, you've probably heard it, that the glass in medieval cathedral windows is thicker at the bottom than at the top because the glass has been slowly flowing downward over hundreds of years, like an incredibly slow liquid. It's a beautiful idea. It's also almost certainly wrong, or at least wildly misleading. The thickness variations in old cathedral glass are most likely just artifacts of the manufacturing process. Medieval glassmakers used a technique called crown glass or broadsheet glass, and the results were never perfectly uniform. Glaziers probably just installed the thicker edge at the bottom because it made structural sense. And even if glass does flow, the timescales involved at room temperature would be so astronomically long, longer than the age of the universe by some calculations, that you'd never see it happen in a cathedral window. But the myth persists because it touches something real. There are materials that seem solid, that feel solid, that behave as solid for all practical human purposes, but that are, on long enough timescales, flowing, slowly, imperceptibly, but genuinely flowing. And that brings us to pitch. Pitch. You might not know exactly what pitch is, and that's fine, because most people don't encounter it in their daily lives anymore. though for thousands of years it was one of the most important materials in human civilization. Pitch is the name given to a range of very thick, very dark tar-like substances derived from plant resins, or more commonly, from the distillation of coal tar or petroleum. The ancient Babylonians used it to waterproof boats. Noah's Ark, in the biblical story, was sealed with pitch. The Romans used it to line aqueducts and seal amphorae. Sailors caulked the seams of wooden ships with it for centuries. The phrase pitch black comes from the color of the stuff, and the word pitch for a ship's rocking motion may be related to the process of applying hot pitch to a hull while the vessel swayed. By the time the Industrial Revolution rolled around, coal tar pitch was everywhere. It was a byproduct of the coal gas industry. When you heated coal to extract gas for lighting and heating, you got this thick, black, sticky residue left over. And people found uses for it: road surfaces, roofing material, waterproofing, insulation. It was cheap, it was abundant, and it had this remarkable property. At room temperature, it seemed completely, utterly solid. You could hit it with a hammer and it would shatter like glass. You could snap a piece in two. It felt brittle and hard and as solid as any rock you'd ever held. But if you left it alone, if you just set a lump of pitch on a table and walked away and came back in a very, very long time, something strange would happen. It would flatten. Slowly, almost immeasurably slowly, the pitch would begin to spread under its own weight. It was flowing. This substance that shattered like glass when you struck it was, given enough time, behaving like a liquid with a viscosity roughly 100 billion times that of water, but a liquid nonetheless. And this is where we meet the man who decided to prove it. Thomas Parnell was a professor of physics at the University of Queensland in Brisbane, Australia. He was born in England in 1881, studied at Cambridge, and came to Australia to take up his position in 1918, just as the First World War was ending. Queensland in those days was not exactly the center of the scientific world. It was remote, it was hot, and the university was young. It had only been founded in 1909. Parnell was the kind of physicist who cared deeply about teaching, about making abstract concepts tangible and real for his students. He wasn't chasing Nobel Prizes. He wasn't trying to revolutionize physics. He just wanted to demonstrate something that he thought was beautiful and important and underappreciated, that the distinction between solid and liquid is not always as clear as it seems. So in 1927, Parnell took a quantity of pitch, heated it up, poured it into a glass funnel with a sealed stem, and let it settle. He let it sit for 3 years. 3 years, just to let the pitch fully settle into the funnel and reach something like equilibrium. Then, in 1930, he cut the sealed stem of the funnel open, and he waited. Think about what he was doing. He was setting up an experiment whose results he knew he would probably never fully see. He was 39 years old when he poured the pitch, 48 when he opened the stem, and the pitch moves so slowly that a single drop takes roughly a decade to form and fall. He was building something for the future, something that would outlast him, and he knew it. There's something quietly profound about that. A scientist who plants a tree whose shade he knows he'll never sit in. The funnel was placed on a stand with a beaker beneath it to catch the drops, and it was put on display in the foyer of the physics department. No special climate control, no sealed chamber, just sitting there in the Brisbane air, which, if you've ever been to Brisbane, you know can be brutally hot and humid in summer. The temperature fluctuations would actually matter as it turns out, because pitch is sensitive to temperature. Warmer conditions make it flow a little faster. Cooler conditions slow it down. But Parnell didn't try to control for that. This wasn't meant to be a precision measurement of viscosity. It was meant to be a demonstration, a slow, patient, elegant demonstration that pitch is a fluid. And so it began. The pitch started to move. Not in any way you could see, not on any time scale that a human being standing there watching would ever notice, but it was moving. The bulge at the bottom of the funnel began, over months and years, to slowly extend downward, forming a pendant drop, like honey dripping from a spoon, but slowed down by a factor of billions. The first drop fell in December of 1938, 8 years after the stem was opened. 8 years for a single drop of this material to stretch and neck and finally pinch off and fall into the beaker below. Parnell recorded it. The second drop fell in February of 1947. Another 8 years, give or take. Then a third in April of 1954. Parnell didn't see that one. He had died in 1948, just a year after the second drop fell. He was 67 years old, and he had lived long enough to see exactly 2 drops fall from his experiment. 2 data points in 20 years of watching. Now, here's where you might expect the story to end. The professor dies, the experiment gets cleaned up, someone throws it in a closet. That's what happens to most demonstration apparatus when the person who cared about it is gone. But that's not what happened. The pitch drop experiment just kept going. It sat there in the physics department, and the pitch kept flowing, and drops kept forming. And someone, always someone, kept watching, or rather kept checking in, because this is the kind of experiment where watching is almost useless. The drops fall so rarely and so unpredictably that the odds of actually being present at the moment of a drop are vanishingly small. And this is where the experiment starts to take on a character of its own, almost like a personality. Because it has this maddening, almost mischievous quality, nobody has ever actually seen a drop fall. Not Parnell, not his successors, not the cameras that were eventually set up to watch it. And the story of those near misses, those agonizing almosts, is one of the most wonderfully human tales in all of science. But let me tell you about the pitch itself first, because to really understand why this experiment matters, why it's more than just a quirky curiosity, you need to understand something about how materials behave at the boundary between solid and liquid. And that takes us into the strange and beautiful world of rheology. Rheology. It's not a word most people know, but it's the science of how materials flow and deform. The name comes from the Greek word rheo, meaning to flow, and it was actually coined in the late 1920s, right around the time Parnell was setting up his experiment, by a chemist named Eugene Bingham. And Bingham chose the name partly inspired by a quote attributed to Heraclitus, the ancient Greek philosopher, "Panta rhei, everything flows," which is, in a sense, exactly what the pitch drop experiment is trying to show you. Everything flows if you wait long enough. The simplest way to think about rheology is through viscosity. Viscosity is just a measure of a fluid's resistance to flow. Water has a low viscosity. It flows easily, sloshes around, pours quickly. Honey has a higher viscosity. It's thick and slow. Motor oil is somewhere in between, and its viscosity changes with temperature, which is why your car's engine behaves differently on a cold morning. These are all obviously liquids. But viscosity is a spectrum, and it extends far, far beyond what we normally think of as liquid. Glaciers flow, the Earth's mantle flows. The solid rock beneath your feet is, on timescales of millions of years, churning and convecting like a pot of very, very slow soup. Even the steel in a bridge, if you load it and wait long enough, will creep, deform slowly under sustained stress. The question is never really whether something flows. The question is, how fast and under what conditions, and what happens when you push a material past the point where it can resist. And that's where things get really interesting, because not all materials play by the same rules when it comes to flow. See, the simplest kind of fluid, water for instance, follows a nice, clean relationship. You push it, it flows. You push it twice as hard, it flows twice as fast. The relationship between the force you apply and the rate of flow is perfectly linear, perfectly proportional. Fluids like that are called Newtonian fluids, named after Isaac Newton, who was actually one of the first people to think carefully about viscosity way back in the late 1600s. And for a lot of everyday liquids, water, air, simple oils, Newton's model works beautifully. But pitch is not a Newtonian fluid, not even close. Pitch belongs to a much stranger category of materials, and this is where rheology really earns its keep. Some materials don't flow at all until you apply enough force to overcome a kind of internal threshold, a yield stress. Below that threshold, they behave like solids. Above it, they start to flow. Think of ketchup. You know how ketchup just sits there in the bottle, stubbornly refusing to move, and then suddenly it all comes out at once. That's because ketchup has a yield stress. It's acting like a solid until you shake the bottle hard enough, and then it transitions into flowing behavior. Toothpaste does the same thing. It holds its shape on your brush, but it flowed just fine when you squeezed the tube. Materials like these are sometimes called Bingham plastics, named after that same Eugene Bingham who coined the word rheology. And pitch has some of these characteristics, though it's even more complicated than that, because pitch also behaves differently depending on how long you've been applying force to it, and how quickly, and at what temperature, and whether you applied force yesterday and then stopped. Its behavior has a kind of memory. It's what scientists call a viscoelastic material. It has properties of both a viscous fluid and an elastic solid, and which behavior dominates depends entirely on the timescale you're looking at. Here's a thought experiment that might help. Imagine you have a block of pitch sitting on a table. If you take a hammer and hit it, it shatters. Clean, brittle fracture, like glass. On that timescale, milliseconds, pitch is a solid, an extremely brittle solid. But now imagine you just leave that same block of pitch sitting on the table for a few months. Come back and you'll find it's flattened out. It's flowed under nothing more than its own weight and the gentle, patient pull of gravity. On that timescale, months, years, pitch is a liquid. Same material, completely different behavior, depending entirely on how fast you interact with it. There's actually a beautiful way to quantify this, and it's called the Deborah number. It was proposed by a rheologist named Marcus Reiner in 1964, and he named it after the biblical prophetess Deborah, because of a passage in the book of Judges where she sings that the mountains flowed before the Lord. Reiner loved that image, mountains flowing, because it captured exactly the idea he was trying to formalize. The Deborah number is simply the ratio of a material's relaxation time to the time you spend observing it. If the Deborah number is high, meaning the material's internal relaxation time is much longer than your observation window, the material looks solid. If the Deborah number is low, meaning you're watching for much longer than the material needs to relax, it looks like a liquid. And the profound implication is that the distinction between solid and liquid isn't really about the material itself. It's about the relationship between the material and the observer. It's about time. And that, when you think about it, is exactly what Thomas Parnell's experiment is sitting there quietly demonstrating, decade after decade. Pitch has a very long relaxation time. If you watch it for a minute, it's a solid. If you watch it for a decade, it's a liquid. The experiment is a physical embodiment of the Deborah number, made real and visible and dripping slowly in a university hallway. But let's come back to that hallway, because the story of what happened to the experiment after Parnell died is in its own way just as fascinating as the physics. So Parnell passed away in 1948, just a year after the second drop fell. The third drop fell in 1954, and by that point, nobody was really paying much attention. The experiment was just sitting there in the department, an odd curiosity, a relic from a professor most of the newer staff had never met. It wasn't being monitored in any formal way. There were no cameras, no sensors, no graduate students assigned to watch it. It was just a funnel full of pitch on a shelf, doing its thing, and every now and then, someone would notice that the drop had changed shape, or that a new one had separated from the mass above. The fourth drop fell in 1962, the fifth in 1970, the sixth in 1979. And here's something remarkable about all of those drops. Every single one of them fell when nobody was watching. Not one person in all those decades actually saw a drop detach and fall. Think about that. By 1979, the experiment had been running for nearly 50 years, and 6 drops had fallen. And the moment of separation, that instant when the drop finally lets go, had never been witnessed by a single human being. Now, part of this makes sense when you think about the timing. Each drop takes roughly 8 to 12 years to form and fall. But the actual moment of separation, the pinch-off, when the thin neck of pitch connecting the drop to the funnel finally stretches too thin and breaks, that happens relatively quickly. Not instantaneously, but over a period of maybe a few hours at most. So you've got this incredibly long buildup, years and years of slow, imperceptible deformation, and then a comparatively brief moment of release. The odds of someone happening to walk by at exactly the right time were always pretty slim, especially for an experiment that nobody was formally watching. But by the late 1970s, the experiment was starting to attract attention. A physics professor named John Mainstone had joined the University of Queensland in 1961, and at some point, he became aware of this strange old apparatus sitting in the department. Mainstone became the experiment's custodian, its champion, its devoted guardian. He recognized what Parnell had started, and he made it his mission to care for the experiment, to document it properly, and, above all, to finally witness a drop fall. And this is where the story takes on an almost tragicomic quality, because John Mainstone spent the better part of his career trying to see a drop fall, and he never did. Not once. The universe seemed to conspire against him, with an almost mischievous persistence. The 7th drop fell in 1988. Mainstone had been watching the experiment carefully, tracking the slow elongation of the pendant drop, trying to estimate when it would finally let go. But he stepped away. The exact circumstances vary a little depending on which account you read, but the essential fact is the same. He wasn't there when it happened. He came back, and the drop was sitting in the beaker below the funnel, freshly separated, and he'd missed it. So for the 8th drop, Mainstone decided he would not be caught off guard again. By the late 1990s, the drop was clearly forming, elongating, getting ready. And this time, they set up a camera, a proper webcam, connected to the internet, broadcasting live to anyone in the world who wanted to watch Pitch not move. It was one of the earliest webcam experiments, actually. This was the late 90s, when the internet was still relatively young, and the idea of pointing a camera at something and letting people watch it online was still novel. And people did watch. The Pitch Drop webcam became a minor internet sensation. Here was this ancient experiment, this absurdly slow drama, playing out in real time on screens around the world. The 8th drop fell in November 2000, and the camera missed it. The recording equipment malfunctioned at the critical moment. Some accounts say there was a power outage. Others say the camera's feed simply failed. Either way, when the drop finally separated after its long, patient journey, the camera wasn't recording. Mainstone, once again, wasn't in the room. Nobody saw it. You can imagine how that felt. Decades of waiting, a camera specifically installed to capture the moment, and a technical failure at precisely the wrong instant. There's something almost poetic about it, in a painful sort of way. As if the experiment itself was determined to keep it secret, to guard the moment of separation as something private, something not meant to be observed. And this is where you start to wonder whether there's something deeper going on, not in any mystical sense, but in a practical, physical sense. Why is the moment of drop separation so hard to catch? Part of the answer is just probability and human attention spans, but part of it is also about the nature of the flow itself. The way pitch deforms is so extraordinarily slow that there's no obvious visual cue telling you this is about to happen. The drop elongates over months, the neck thins over weeks, and then at some point the neck becomes thin enough that the remaining pitch can no longer support the weight of the drop below, and it lets go. But that final failure happens on a timescale that's fast compared to the formation process, yet still slow compared to, say, a water drop falling from a faucet. It's an ambiguous tempo. Too slow to be dramatic, too fast to be predictable. After the 8th drop, Mainstone and his colleagues upgraded their setup. Better cameras, backup power, redundant recording systems. They were not going to let technology fail them again. The 9th drop began its long formation, and the world settled in to wait. By this point, the pitch drop experiment had become genuinely famous. In 2005, Mainstone and the late Thomas Parnell were jointly awarded the Ig Nobel Prize in Physics. That's the award given for research that, as they put it, first makes people laugh and then makes them think. Mainstone accepted in person. Parnell, of course, had been dead for nearly 60 years, but the recognition was fitting. The experiment was a joke and a profound statement about the nature of matter, all at once. And Mainstone kept watching. He kept visiting the experiment, kept checking the cameras, kept waiting for that 9th drop. He'd been the experiment's guardian for over 50 years by this point. He'd dedicated a significant portion of his professional life to this one, patient, seemingly absurd act of observation. And on August 23, 2013, John Mainstone died. He was 78 years old. The 9th drop had not yet fallen. It fell about a year later, in April 2014, and this time, finally, after 84 years, it was captured on camera. A live stream recorded the moment of separation, and people around the world watched the footage. It wasn't dramatic. It was, in fact, almost anticlimactic, a slow, silent stretching, a thinning of the neck, and then a gentle release. The drop settled into the beaker below with no sound, no splash, no fanfare, just gravity and patience and the quiet persistence of a material doing what materials do when you give them enough time. But Mainstone never saw it. The man who had spent more than half a century waiting for that moment was gone, and the drop fell without him. There's a sadness in that, a real human sadness that goes beyond physics and into something about devotion and time and the things we choose to care about even when the world thinks we're a little bit crazy for caring. And yet, the experiment continues. It's still there, in a climate-controlled display at the University of Queensland, still dripping, still being watched, still being measured. The 10th drop is forming right now, as you listen to this, elongating imperceptibly under the pull of gravity. And the physics department has better cameras now, better sensors, better everything. They'll catch the next one. But the experiment has already taught us something that no single drop could capture on its own, something about the way materials exist on a continuum between solid and liquid, something about how the boundary between those states is not a line, but a blur, a gradient, a question of time and perspective. And that's really the heart of it, isn't it? Whether something is solid or liquid depends on how long you're willing to watch. It depends on the time scale of your observation compared to the time scale of the material's response. And once you internalize that idea, once you really sit with it, it starts to change the way you think about everything around you. Take glass. Ordinary window glass. We talked earlier about how the old myth says medieval cathedral windows are thicker at the bottom because the glass has been flowing downward for centuries, and we said that's not true. The thickness variations come from how the glass was made, not from flow. But here's what's subtle about that myth. The reason it persists, the reason it sounds so plausible to so many people, is that glass really is, in a technical sense, not a true crystalline solid. It's an amorphous solid. Its molecules are arranged in a disordered way, more like a liquid that got frozen in place than like a crystal with neat rows and columns. And that disordered structure raises a genuinely fascinating question in physics, one that scientists have been arguing about for over a century. Is glass a solid? Or is it an extremely viscous liquid? The answer, as you might expect by now, is that the question itself is a bit misleading. Glass is glass. It's its own thing. But let's unpack why, because the physics here is beautiful, and it connects directly to what the pitch drop experiment is quietly demonstrating. When you cool a liquid down, normally what happens is that at some specific temperature, the melting point, the molecules snap into an ordered crystalline arrangement. Water does this at 0 degrees Celsius. It goes from liquid to ice, and there's a sharp transition. The molecules reorganize. The density changes. The heat capacity changes. It's a first-order phase transition, which is physics speak for a clean, well-defined boundary between two states. One moment, it's water. The next, it's ice. You can point to the exact temperature where it happens, but some materials don't do that. Some materials, when you cool them, just get thicker and thicker and thicker. The molecules slow down. They become more sluggish. They have a harder time rearranging themselves, but they never actually snap into a crystal. They never find that ordered arrangement. Instead, they just gradually become so viscous that they effectively stop flowing, not because they've changed state in any fundamental structural way, but because their molecules have simply run out of energy to move past each other. The structure stays disordered, stays liquid-like in its arrangement, but the behavior becomes solid-like. This is the glass transition, and the temperature at which it happens is called, naturally enough, the glass transition temperature. And here's what's really interesting about it. The glass transition temperature isn't a fixed, fundamental property of the material the way a melting point is. It depends on how fast you cool the liquid. Cool it slowly, and the molecules have more time to rearrange, so they stay liquid-like to a lower temperature. Cool it quickly, and they freeze into their disordered state sooner at a higher temperature. The glass transition is not a phase transition in the traditional thermodynamic sense. It's a kinetic phenomenon. It's about how fast things are happening relative to how fast the material can respond. Sound familiar? It should. It's the Deborah number all over again, just wearing different clothes. So glass, the stuff in your windows, your drinking glasses, your phone screen, exists in this strange in-between state. Structurally, it looks like a liquid. Its molecules are jumbled, disordered, with no long-range crystalline order. But mechanically, it behaves like a solid. It's rigid, it's brittle, it shatters when you hit it. And the Pitch and Thomas Parnell's experiment is doing something conceptually similar, just at a different point on the spectrum. Pitch is an amorphous material with a viscosity so high that it behaves like a solid on human timescales. You can shatter it with a hammer, but it flows, undeniably flows, when you give it years and decades. The difference between pitch and window glass is really just a matter of degree. Window glass has a viscosity so astronomically high at room temperature, something like 10 to the power of 20 Pascal seconds, maybe higher, that the time it would take to flow even a detectable amount is longer than the age of the universe. Literally, people have done the calculations. For cathedral glass to have flowed noticeably thicker at the bottom over 800 years, the viscosity would need to be roughly 10 to the power of 12 Pascal seconds. The actual viscosity of soda-lime glass at room temperature is billions of times higher than that. So no, your windows are not flowing. Not in any meaningful sense. Not in any time scale that matters to you or to the earth or to the sun. But pitch? Pitch has a viscosity of around 200 billion Pascal seconds, roughly 10 to the 11. That's enormously viscous, absurdly viscous, but it's within the range where gravity can do its work over years. That's why the experiment works. That's why drops fall roughly once a decade. The pitch is viscous enough to seem solid, but not so viscous that flow becomes geologically or cosmically slow. It sits in this sweet spot where human patience, or at least institutional patience, can actually observe the transition from apparent solidity to undeniable flow. And this is where the experiment transcends being a curiosity and becomes something genuinely important for physics. Because that continuum between solid and liquid, that gradient we keep talking about, is not just an abstract idea. It's central to understanding an enormous class of materials that don't fit neatly into the categories we learned in school. Polymers, gels, biological tissues, magma, the Earth's mantle, peanut butter, if you want to be playful about it. All of these materials have complex, time-dependent mechanical behavior. They're not simply solid or simply liquid. They respond differently depending on how quickly you push them, how long you wait, how much stress you apply. Think about the Earth's mantle, that thick layer of rock between the crust and the core. On short timescales, it's solid. Seismic waves from earthquakes travel through it as shear waves, and shear waves can only propagate through solids. If the mantle were a liquid, those waves would stop dead. So by that measure, you're standing on solid rock all the way down. But on timescales of millions of years, The mantle flows. It convects. Hot rock rises from near the core, spreads laterally, cools, and sinks back down, driving the motion of tectonic plates, building mountains, opening oceans. The mantle is solid and liquid simultaneously, depending entirely on the timescale you choose to care about. Its Deborah number for earthquake waves is enormous. It's a solid. Its Deborah number for continental drift is tiny. It's a fluid. Same material. Two completely different identities, separated only by time. And this is the kind of thinking that the pitch drop experiment makes visceral. It takes an abstract concept from rheology and material science and turns it into something you can watch, or almost watch, something you can point a camera at and say, look, there it is, a material being both things at once, caught in the act of defying our neat categories. Now, the University of Queensland experiment is the most famous, but it's not the only one. And this is worth knowing about, because the parallel experiments tell us something important about reproducibility and about how different conditions change the behavior of this strange material. There's an experiment at Trinity College Dublin that's been running even longer. It was set up in 1944 by a physicist there, and it sat largely forgotten in a display case in the physics department for decades. Nobody was really paying attention to it. Nobody had documented when the drops fell. It was just sitting there, doing its thing, dripping pitch into a beaker while students walked past it on their way to lectures. Then in July 2013, just about a month before John Mainstone died, actually, which is a poignant bit of timing, physicists at Trinity realized they had a webcam on it, and they captured a drop falling. So technically, the Trinity College experiment beat Queensland to the punch in terms of getting a drop on video. The Dublin pitch was a slightly different formulation, and the conditions were different. The building wasn't climate controlled in the same way, so temperature fluctuations over the decades likely affected the flow rate. But the basic phenomenon was the same: pitch, funnel, gravity, patience. There's something wonderful about the fact that these experiments exist in multiple places, set up by different people in different decades, all quietly demonstrating the same fundamental truth about materials. It's like having multiple clocks all ticking at slightly different rates, but all telling you the same thing about the nature of time. And the Queensland experiment has gotten more sophisticated over the years. After the 9th drop fell in 2014 and was successfully recorded, the physics department didn't just sit back and wait for the 10th. They started instrumenting the experiment more carefully. Temperature sensors, more precise cameras, better environmental controls. Because one of the things they've realized is that the rate of dripping is exquisitely sensitive to temperature. Even a change of a few degrees can significantly alter the viscosity of the pitch, which changes how fast it flows, which changes when the next drop will fall. The old drops fell at irregular intervals, partly because the building's temperature wasn't controlled. Brisbane gets hot in summer, and air conditioning wasn't always consistent. When they moved the experiment into a climate-controlled case, the conditions became more stable, and the predictions for the next drop became, in principle, more reliable. But predicting exactly when a drop will fall is still remarkably difficult. And the reason goes back to something we touched on earlier: the mechanics of the separation itself. The drop doesn't just fall when it reaches a certain weight. What happens is more nuanced than that. As the pitch slowly extrudes from the funnel, it forms a pendant drop, a teardrop shape hanging from the stem. The weight of the pendant drop pulls it downward, and the viscous resistance of the pitch in the neck, That thin thread connecting the drop to the bulk material above holds it up. As the drop grows heavier, the neck gets thinner, and as the neck gets thinner, the stress on it increases, which makes it stretch faster, which makes it thinner still. It's a positive feedback loop, a runaway process. For years, the neck thins almost imperceptibly. Then, in the final stages, things accelerate. The last millimeter of thinning might happen over weeks or days rather than years. And the final pinch-off, the actual moment of separation, might happen over just seconds. This is what makes it so hard to predict and so hard to witness. You have this enormously long, boring buildup where essentially nothing visible is happening, followed by a relatively sudden event. It's like watching a pot that takes a decade to boil. You can't stare at it the whole time, and for most of that time, there's genuinely nothing to see. The pitch looks the same from one month to the next, but underneath that apparent stillness, molecules are sliding past each other, stress is accumulating in the neck, and the geometry is evolving in ways that are heading inexorably toward a moment of catastrophic failure. And that word, catastrophic, might sound dramatic for a blob of tar dripping off a funnel, but in engineering and physics, it has a precise meaning. A catastrophic failure is one where the system transitions from a stable state to an unstable one, and once that transition begins, it accelerates rather than slowing down. The neck of the pitch drop is a textbook example. For years, the system is quasi-stable. The neck is thinning, yes, but so slowly that at any given moment, the forces are nearly in balance. Then, at some critical geometry, some critical ratio of neck diameter to drop weight, the balance tips and the process runs away. The neck can no longer thin gradually enough to redistribute the stress. It pinches, and the drop falls. Now, here's what's really beautiful about this. That pinch-off process, the way a thin thread of fluid necks down and snaps, isn't unique to pitch. It happens every time you turn off a faucet, and that last little thread of water breaks. It happens when honey drips off a spoon. It happens when inkjet printers fire droplets onto paper. It happens when molten glass is drawn into optical fibers. The physics of how a fluid thread breaks apart is one of those gorgeous universal problems that shows up everywhere, at every scale, and the mathematics that describe it are surprisingly deep. The study of this goes back further than you might expect. There's a Belgian physicist named Joseph Plateau, the same Plateau who gives his name to Plateau's laws of soap films, who was investigating fluid instabilities back in the 1840s. Plateau noticed that a long cylinder of fluid is inherently unstable. If you could somehow create a perfectly cylindrical column of water floating in zero gravity, it wouldn't stay cylindrical for long. Any tiny perturbation, any slight bulge or narrowing, would grow. The slightly fatter regions would get fatter, the slightly thinner regions would get thinner, and eventually the cylinder would break up into a series of droplets. Lord Rayleigh formalized this mathematically in the 1870s and 1880s, and today we call it the Plateau-Rayleigh instability. You've seen it 1,000 times without knowing its name. Next time you watch water streaming from a garden hose, notice how a smooth stream eventually breaks up into droplets at some distance from the nozzle. That's Plateau-Rayleigh. The stream is a cylinder of fluid, and it's unstable, and surface tension is what drives the breakup. Surface tension. Let's sit with that for a moment, because it's doing something subtle and important. You probably think of surface tension as the thing that lets water bugs walk on ponds, or that makes small droplets spherical, and it is those things. But surface tension is also a force that has opinions about geometry. Specifically, surface tension wants to minimize the total surface area of a fluid for a given volume. A sphere has the smallest surface area for a given volume. That's why raindrops are roughly spherical, why bubbles are round. Now think about that cylinder of fluid. A long, thin cylinder has a lot of surface area relative to its volume. If that same volume of fluid rearranged itself into a series of spherical droplets, the total surface area would actually be less. So surface tension is constantly trying to break up cylinders into spheres. It's an energy minimization problem. The cylinder is a higher energy state. The chain of droplets is a lower energy state. And any perturbation that moves the system toward that lower energy state will be amplified. In the pitch drop experiment, the neck connecting the pendant drop to the funnel is essentially a short cylinder of very viscous fluid, and it's subject to the same instability. Surface tension wants to pinch it off. Gravity is pulling the drop down, stretching the neck, making it thinner, and the viscosity of the pitch is the only thing resisting. It's the braking force, the thing that makes this process take years instead of milliseconds. In water, a thread of comparable dimensions would snap in a fraction of a second. In pitch, with a viscosity roughly 100 billion times greater than water, the same fundamental process plays out over a time frame that spans human careers. And here's the kicker. The very final moment of pinch-off, regardless of the fluid's viscosity, follows a universal scaling law. In the 1990s, physicists and applied mathematicians, people like Jens Eggers, who did some of the foundational theoretical work on this, showed that as a fluid neck approaches the moment of breakup, the dynamics become self-similar. What that means is that if you zoom in on the neck as it gets thinner and thinner, the shape looks the same at every scale. The profile of the neck near the pinch point follows a mathematical form that doesn't depend on the specific fluid or the specific geometry of the experiment or how the drop was formed. It's universal. The only things that matter are the fluid's viscosity, its surface tension, and its density. Everything else washes out. Think about what that means. Whether you're watching pitch drip from a funnel in Brisbane, or ink ejecting from a printer nozzle in Tokyo, or a strand of mozzarella stretching between a slice of pizza and your mouth. At the very last instant before the thread breaks, the physics converges to the same mathematical description. The details of how you got there don't matter. The end game is the same. There's something almost philosophical about that, isn't there? All these wildly different systems, operating at wildly different speeds and scales, and they all arrive at the same final act. Eggers published a landmark paper in 1993, in Physical Review Letters if you're curious, that laid out the theory for how Newtonian fluid threads break up. The neck radius decreases linearly with time as you approach the breakup moment. The shape near the pinch point is asymmetric. It's not a simple hourglass. There's a long, thin thread on one side and a more bulbous shape on the other. And the whole thing is governed by a balance between inertia, viscosity, and surface tension, with different balances dominating at different stages. Early on, when the neck is still relatively thick, viscosity and surface tension are the main players. Very close to breakup, inertia starts to matter too, even in viscous fluids. The interplay shifts as the length scales shrink. For something like pitch, though, the story is a little different, because pitch isn't purely Newtonian. Remember our earlier conversation about non-Newtonian fluids? about how some materials change their behavior depending on how fast you deform them? Pitch is viscoelastic. At the very slow deformation rates during most of the neck thinning process, it behaves more or less like an extremely viscous Newtonian fluid. But in those final moments, when the neck is thinning rapidly, the deformation rate spikes, and the elastic character of the pitch might start to matter. The material might store some energy elastically, like a spring, rather than dissipating it all as viscous flow. This could change the shape of the neck near breakup, could change the scaling laws. It's one of the reasons the pitch drop experiment remains scientifically interesting even today. It's not just a curiosity or a demonstration. It's a real test case for theories of how complex fluids behave under extreme conditions. And extreme is the right word, even though everything looks so placid. The strain rate in the neck just before pinch-off, the rate at which the material is being stretched, can be enormous compared to the strain rates during the years of slow extrusion. You go from a regime where the pitch is barely moving to one where it's deforming rapidly, all within the same experiment, all within the same material. It's like watching a glacier suddenly become a river. The material hasn't changed. The conditions have. Now let me bring this back to something practical, because all of this pinch-off physics isn't just academic. It's central to a huge range of technologies. Inkjet printing, which I mentioned, that's a multi-billion-dollar industry that depends entirely on controlling how tiny droplets of fluid form and break away from nozzles. The quality of every printed page, every photograph from an inkjet printer, depends on engineers understanding exactly how fluid threads neck down and snap, how satellite droplets form. Those are the tiny extra droplets that sometimes form when a thread breaks in more than one place, and how to suppress them. If you get unwanted satellite droplets, you get fuzzy text, blurred images, wasted ink. Fiber optics rely on a related process. When you draw optical fiber, you're pulling molten glass, a viscous fluid, into an incredibly thin, incredibly long thread. You need that thread to remain stable, to not break up via the Plateau-Rayleigh instability. So engineers have to understand the conditions under which a viscous thread remains stable and the conditions under which it fragments, and they have to control temperature and pulling speed and glass composition to stay on the right side of that boundary. Spray painting, fuel injection in engines, pharmaceutical aerosols, even the way fertilizer is applied to crops. All of these involve controlling how fluids break up into droplets. And the fundamental physics, the deep mathematics, is the same physics that governs that quiet, almost imperceptible thinning of the pitch neck in a dusty display case in Brisbane. There's something wonderful about that connection. Thomas Parnell, setting up his experiment in 1927, couldn't have known that the simple act of letting pitch drip through a funnel would connect to questions that engineers and physicists would still be wrestling with a century later. He was trying to demonstrate a simple point for his students, that some things that seem solid can flow, and he succeeded at that. But the experiment he created turned out to be richer than he imagined, touching on questions about the nature of fluids, the meaning of viscosity, the universality of physical law, and the strange way that timescale shapes our perception of reality. And speaking of timescale shaping perception, this is something worth lingering on, because it connects the pitch drop experiment to a much broader idea in science and engineering. We talked earlier about the Deborah number, that ratio of a material's relaxation time to the observation time. High Deborah number, the material seems solid. Low Deborah number, it seems liquid. But there's a deeper point lurking here, one that goes beyond material science. The Deborah number is really about the relationship between the observer and the observed. It's about how the time scale of your attention, your patience, your lifespan, your funding cycle, your instrument's recording window, shapes what you're able to see and understand about a system. This shows up everywhere in engineering and science. Think about fatigue in metals. A bridge might carry traffic for decades, each passing truck applying a tiny stress that's well below the yield strength of the steel. If you tested that steel in a lab, applying that same stress once, nothing would happen. The steel would flex slightly and spring back, perfectly elastic, no damage. But apply that stress 10 million times, 100 million times, and microscopic cracks nucleate and grow. The steel fails, not because any single load was too much, but because damage accumulated over a timescale that's invisible to any single observation. Engineers in the 19th century learned this the hard way, through catastrophic failures of railway axles and bridge components that seemed perfectly sound. August Wöhler, a German railway engineer, spent years in the 1850s and 1860s systematically testing how metals fail under repeated loading, creating what we now call SN curves, stress versus number of cycles to failure. His work revealed a whole world of material behavior that was invisible at short timescales. Or think about corrosion. A steel pipe buried underground might last 5 years or 50 years depending on the soil chemistry, the moisture, the presence of stray electrical currents. The pipe looks fine on day 1, on day 1000. But atom by atom, the iron is oxidizing, the wall is thinning, the process is too slow to see, too slow to feel, but it's relentless. And when the pipe finally bursts, it seems sudden, just like the pitch drop seems sudden when it finally falls. But the failure was decades in the making, happening continuously, hidden by the mismatch between the process timescale and the human attention span. The pitch drop experiment is, in a way, a meditation on this mismatch. It sits there in its case, looking exactly the same from one visit to the next. And it asks you a question. Are you patient enough to see what's really happening? Are you willing to watch on the timescale that the physics demands, rather than the timescale that your schedule allows? For most of us, the answer is no, and that's fine. That's what cameras and sensors are for. But there's something humbling about a physical system that simply refuses to perform on your schedule. It operates on its own clock, indifferent to your curiosity, your career, your lifetime. And that indifference, that quiet stubbornness of the physical world, is actually one of the most important things the experiment has to teach us. Because it's not just about pitch, it's about how we understand anything that moves slower than we do, or faster than we do, or at a scale we can't directly perceive. Think about geology for a moment. The entire science of geology is, in a sense, a long argument about timescale. When people first started seriously studying rocks in the 18th century, they had no framework for deep time. The prevailing assumption, rooted in biblical chronology, was that the Earth was maybe 6,000 years old. And within that framework, the landscape made a certain kind of sense. You needed catastrophic events, great floods, sudden upheavals, to explain how mountains got where they are and why seashells appeared on hilltops. Everything had to happen fast, because there simply wasn't enough time for it to happen slowly. Then along comes James Hutton, a Scottish farmer and physician who spent decades wandering the Scottish countryside, looking at rock formations with fresh eyes. And what Hutton saw, particularly at a place called Siccar Point, on the Berwickshire coast in 1788 changed everything. He found layers of rock that had been deposited horizontally, then tilted vertically, then eroded flat, then buried under new horizontal layers, then uplifted again. The sheer number of sequential processes required to produce that arrangement, deposition, lithification, uplift, erosion, submersion, more deposition, more uplift, implied timescales so vast that Hutton famously wrote he could see no vestige of a beginning, no prospect of an end. The Earth wasn't thousands of years old, it was incomprehensibly ancient, and once you accepted that, once you expanded your Deborah number to accommodate geological time, everything changed. Erosion wasn't a trivial force anymore. Given enough time, water could carve the Grand Canyon. Given enough time, continents could drift. Given enough time, mountains could rise and be worn back down to plains. The physics hadn't changed. The forces were the same ones people had always observed. Rain falling, rivers flowing, frost cracking rock. What changed was the timescale people were willing to consider. And here's what connects this back to our funnel of pitch in Brisbane. The pitch drop experiment is a tiny tabletop version of the same lesson. It asks you to accept that something can be simultaneously solid and liquid, that a material can flow without appearing to move, that a process can be continuous even when every snapshot looks static. It's Hutton's unconformity in a glass case. The forces are small, just gravity pulling on a few hundred grams of pitch. The flow is real but imperceptible, and the timescale is long enough to outlast careers, to outlast lives. Now, I want to take this idea in a slightly different direction, because the pitch drop experiment doesn't just teach us about patience. It teaches us about measurement itself, about what it means to observe a system and how the act of observation, or the inability to observe continuously, shapes what we think we know. Consider this. For the first 70-odd years of the experiment's existence, nobody actually saw a drop fall. Not once. John Mainstone watched and waited and measured and documented, but every single drop found a way to fall when nobody was looking. The 8th drop in November 2000 was particularly painful. There was a camera set up, but the feed malfunctioned at the critical moment. It's almost comical, except it wasn't comical to Mainstone. He'd devoted a significant portion of his professional life to this experiment, and the universe kept denying him the one observation he wanted most. But here's what's interesting from a scientific perspective. Did it matter? Did the fact that no one directly witnessed the drop falling change the scientific value of the experiment? In one sense, no. The drops fell. The timing between drops was recorded. The viscosity could be calculated. The data was the data, whether or not a human eye happened to be watching at the moment of separation. But in another sense, yes, it mattered enormously, because the moment of pinch-off, that final catastrophic necking we talked about earlier, is where some of the most interesting physics happens. The transition from slow creeping flow to rapid separation involves a dramatic change in strain rate, and with it, potentially, a shift in how the pitch behaves. Is it purely viscous in that final moment? Does its viscoelastic character come into play? Does the neck thin symmetrically or asymmetrically? What's the geometry of the pinch point? These are questions you can only answer if you're watching closely, with good instruments, at the right moment. And this is exactly what the University of Queensland team set out to do after John Mainstone's passing in 2013 and the 9th drop's fall in April 2014. They knew the 10th drop was coming. probably sometime in the 2020s, depending on temperature fluctuations, and they wanted to be ready, really ready, not just a webcam this time, but proper scientific instrumentation, high-resolution cameras capable of capturing the geometry of the neck as it thins, temperature sensors to correlate flow rate with ambient conditions. The idea was to transform the experiment from a demonstration, a curiosity, a conversation piece, into an actual source of publishable rheological data. And that transformation is worth pausing on because it reflects something broader about how science works. Thomas Parnell set up the experiment in 1927 as a teaching demonstration. He wanted to show students that pitch, despite feeling solid, could flow. That was the entire point. It wasn't designed to produce precise measurements. The funnel wasn't calibrated. The temperature wasn't controlled. The pitch wasn't a standardized sample with known composition. It was a demonstration, and a brilliant one, but it was never meant to be a precision instrument. Yet over the decades, as the experiment kept running, as drops kept falling, it accumulated a kind of authority simply through persistence. The sheer length of the data set, 9 drops over 87 years, made it unique. No one else had anything like it, and that uniqueness gave it scientific value that Parnell never intended. The spacing between drops, for instance, has not been constant. The early drops fell more frequently, roughly every 8 to 9 years for the first few, while the later drops have been spaced further apart, roughly 12 to 14 years. Why? Part of the answer is that the pitch level in the funnel has dropped, so there's less hydrostatic pressure driving the flow. Part of the answer is that the university installed air conditioning in the building in the 1980s, which lowered and stabilized the ambient temperature, increasing the pitch's viscosity. And part of the answer might be changes in the pitch itself over time, slow chemical changes, loss of volatile compounds, gradual shifts in molecular structure. Teasing apart these factors is genuinely difficult, precisely because the experiment wasn't designed with controlled variables in mind. It's an accidental long-term data set, and like all accidental data sets, it's messy. But messy data from 90 years of continuous observation is still extraordinarily valuable because some things simply cannot be studied any other way. You can't put pitch in a standard rheometer and run it for 9 decades. Well, you could, but no funding agency would pay for it, and no graduate student would wait around for the results. The pitch drop experiment exists in a category of science that's only possible through institutional patience, through a university deciding, generation after generation, that this strange little apparatus in the hallway is worth preserving. And that brings up something I find genuinely fascinating, which is the question of what other long-running experiments exist and what they've taught us. Because the pitch drop isn't entirely alone. There's a small tradition of ultra-long duration experiments in science, and each one has its own story. The Oxford electric bell, for instance, has been ringing almost continuously since 1840. It's a pair of bells powered by what are called dry pile batteries, early electrochemical cells, and a small metal ball bounces back and forth between the bells, driven by electrostatic attraction and repulsion. It's been going for over 180 years. The batteries are still producing enough charge to keep the ball moving, and nobody knows exactly what's inside them, because opening the apparatus to find out would end the experiment. It's a beautiful paradox. The very act of investigating would destroy the thing you're investigating. Then there's the Beverley clock at the University of Otago in New Zealand, a clock that's been running since 1864 without ever being manually wound. It's driven by changes in atmospheric pressure and temperature, which cause a sealed chamber of air to expand and contract, and that expansion and contraction is mechanically coupled to the winding mechanism. It's not perpetual motion. It's drawing energy from its environment, but it's been running for over 160 years, and it raises interesting questions about the boundary between a machine and its surroundings. And there's William Thomson's long-running experiment on the viscosity of glass, which is less famous but directly relevant to our story. Lord Kelvin, because Thomson became Lord Kelvin, was interested in whether glass truly flows at room temperature. He set up experiments with glass fibers under load and measured their deflection over years. His results suggested that glass does creep very slightly under sustained stress, but the rates were so small that they were at the edge of measurability. Modern measurements have pushed those estimates even further down, confirming what we discussed earlier, that window glass at room temperature has a viscosity so astronomically high that any flow is negligible over the age of the universe. But here's what ties all these experiments together, and what makes the pitch drop experiment perhaps the most eloquent of the bunch. Each one is a confrontation between human impatience and physical reality. Each one says, this process is real. It is happening, but it is happening on a timescale that challenges your ability to care, to fund, to maintain attention. And each one rewards patience with insight that couldn't be obtained any other way. The pitch drop experiment has now entered a new phase, with modern instrumentation in place, with the 10th drop slowly forming, the neck gradually thinning, millimeter by millimeter, year by year. The next drop will be the most thoroughly documented in the experiment's history. Researchers will capture the pinch-off in detail that John Mainstone could only dream of. They'll measure the forces, the geometry, the temperature dependence, the rheological transition from creeping flow to catastrophic separation. And when that drop finally falls, probably sometime in the late 2020s, though predicting it precisely is part of the challenge, it will be the first drop in the experiment's century-long history that is fully witnessed, fully measured, fully understood. Or at least, that's the hope. Because if the experiment has taught us anything, it's that pitch has a way of surprising you. And there's another dimension to this surprise, another layer of complexity that we haven't really explored yet, which has to do with what happens when you zoom in, not on the timescale, but on the structure of the material itself. Because pitch isn't just a simple liquid that happens to be very viscous. It's a mixture, a complex blend of hydrocarbons with a range of molecular weights, and its behavior depends not just on temperature and stress, but on its own internal composition, its own molecular architecture. And that architecture is far more interesting than you might expect. Think about it this way. When we say pitch, we're using a single word for something that is really a whole community of molecules. Coal tar pitch, which is what Parnell used, is produced by heating coal in the absence of air, a process called destructive distillation or coking. What comes off is a volatile fraction, the coal tar itself, and when you distill that tar further, removing the lighter oils, what's left behind is pitch. But what's left behind makes it sound like a residue, like the dregs at the bottom of a pot. It's more accurate to think of it as a concentrated ecosystem of aromatic hydrocarbons, molecules built around rings of carbon atoms, fused together in various configurations, decorated with side chains, bridged by oxygen and sulfur and nitrogen atoms, tangled up with each other in ways that depend on how the pitch was made, at what temperature, from what kind of coal. So you've got small molecules in there, things with just 2 or 3 fused rings, relatively mobile, relatively willing to flow past each other, and you've got enormous molecules, polycyclic aromatic hydrocarbons with dozens of rings, sometimes hundreds of carbon atoms that are more like flat sheets or crumpled platelets, and everything in between. The molecular weight distribution of coal tar pitch can span from a few hundred daltons to tens of thousands. That's an enormous range. It's like having a crowd that includes both toddlers and elephants, and asking them all to move through a doorway at the same time. The dynamics of that crowd depend enormously on who's in it and how they interact with each other. Here's what's really clever about thinking of pitch this way. Those big molecules, the high molecular weight polycyclic aromatics, they tend to stack. Their flat ring structures let them pile up like playing cards, held together by what are called pi-pi interactions, which are a kind of weak attractive force between the electron clouds of adjacent aromatic rings. These stacks can form local domains of order within the otherwise amorphous material. They're not crystals exactly. They're too disordered and too small for that. But they're more organized than a random liquid. Researchers sometimes call them mesophase domains or just clusters, and the presence and size and connectivity of these clusters profoundly affect how the pitch behaves. When the pitch is warm, those clusters can break apart more easily. The smaller molecules act as a kind of solvent, keeping everything mobile, lubricating the spaces between the big stacked sheets. The material flows, slowly, but it flows. As it cools, the clusters grow. The small molecules lose their thermal energy and can't disrupt the stacking as effectively, and the whole system stiffens. But it's not a simple on-off transition. It's a gradual shift in the balance of power between the mobile phase and the structured phase, and that balance depends on the exact composition of the pitch. Which molecules are present, in what proportions, with what functional groups. Now, you might be thinking, okay, this is interesting chemistry, but does it actually matter for the experiment? And the answer is yes, quite a lot, because it means that the pitch in the funnel at the University of Queensland is not necessarily the same material today that it was in 1927, not because anyone tampered with it, but because of a process called aging. Over decades, several things can happen to pitch at room temperature. The smaller, more volatile molecules can slowly evaporate from the surface. This is an incredibly slow process. We're talking about molecules with low but non-zero vapor pressures. But over a century, it adds up. As the lighter fractions leave, the average molecular weight of the remaining material increases. The proportion of those big stacking molecules goes up, and the pitch becomes stiffer, more viscous. It's like the toddlers slowly leaving the crowd, and now it's mostly elephants trying to get through the doorway. There's also the possibility of slow chemical reactions. Oxidation, for instance. Pitch exposed to air can undergo gradual oxidative cross-linking, where oxygen bridges form between molecules, tying them together into larger networks. This would also increase viscosity over time. And there's a subtler effect called physical aging, which we touched on earlier when we talked about the glass transition. Materials below their glass transition temperature are not in true thermodynamic equilibrium. They're in a metastable state, slowly relaxing toward a denser, more ordered configuration. For pitch, which sits right in the murky zone between liquid and glass at room temperature, this kind of structural relaxation could be happening continuously, decade after decade, gradually changing the material's properties, even without any chemical change at all. So when researchers look at the intervals between drops and notice that they've been getting longer, The first few drops fell roughly every 8 to 9 years, while more recent ones have taken 12, 13, even 14 years. The obvious explanation is the air conditioning installed in the building in the 1980s, which lowered the ambient temperature and increased viscosity. And that's certainly a big factor. But it might not be the whole story. Some of that slowing could be the pitch itself, changing, aging, losing its lighter fractions, cross-linking, densifying. Disentangling these effects is genuinely difficult because you can't exactly take a sample out of the funnel to test without disturbing the experiment. It's a measurement problem wrapped inside a material science problem wrapped inside a conservation problem. And this is where the pitch drop experiment starts to connect to something much larger in material science, something that engineers and scientists deal with all the time, but rarely get to study on such long timescales. The question of how materials change over the course of their service life. Think about the concrete in a bridge. When it's first poured and cured, it has certain properties, a certain compressive strength, a certain porosity, a certain chemical composition. But over decades, carbon dioxide from the atmosphere slowly diffuses into the concrete and reacts with the calcium hydroxide, converting it to calcium carbonate in a process called carbonation. This gradually changes the pH of the concrete, and when the carbonation front reaches the steel reinforcing bars, those bars lose their protective alkaline environment and begin to corrode. The corrosion products expand, cracking the concrete from within. The bridge that was perfectly sound at year 1 is compromised at year 50, not because of any single dramatic event, but because of slow, relentless chemical change. Or think about the polymers in electrical cable insulation. When those cables are first installed in a nuclear power plant, the insulation is flexible, tough, resilient. But over 30, 40 years of exposure to low-level radiation and elevated temperatures, the polymer chains slowly break, a process called chain scission, or they cross-link in ways that make the material brittle. The insulation that was designed to last the lifetime of the plant might start cracking and failing right when the plant operators are hoping to extend its license for another 20 years. Understanding how that degradation happens, predicting its rate, knowing when the material will cross the line from acceptable to dangerous, that's a problem that requires exactly the kind of long-duration observation that the pitch drop experiment embodies. And here's the thing that makes this so hard. Accelerated aging tests, where you crank up the temperature or the radiation dose or the chemical exposure to simulate decades of aging in a matter of months, are useful, but they're also treacherous. Because the mechanisms of degradation often change with conditions. A polymer that degrades by chain scission at low temperatures might degrade by cross-linking at high temperatures. A concrete that carbonates slowly and uniformly at ambient conditions might develop completely different crack patterns when you try to speed up the process in a laboratory. The relationship between accelerated time and real time is not always linear, not always predictable. Sometimes the only way to know what 30 years does to a material is to wait 30 years, which is exactly what the pitch drop experiment has done. Accidentally, inadvertently, without anyone planning it that way, Parnell's little teaching demonstration has become one of the longest continuous material aging studies in existence. The pitch in that funnel has been sitting at roughly room temperature, exposed to air under a slowly decreasing gravitational load for nearly a century. It is its own aging experiment, and the fact that the drop intervals have changed over time is data. Real, irreplaceable, century-scale data about how a complex, amorphous material evolves. This connects to an even broader idea in engineering, one that has become increasingly important in the 21st century, the concept of structural health monitoring. The idea is simple in principle. but enormously challenging in practice. Instead of waiting for something to fail and then figuring out what went wrong, you instrument the structure, the bridge, the pipeline, the aircraft fuselage, the wind turbine blade, with sensors that continuously monitor its condition. Strain gauges, accelerometers, acoustic emission sensors, fiber optic cables that can detect tiny changes in temperature or deformation along their entire length. You build a picture of how the structure is behaving in real time, and you look for deviations from the expected pattern that might signal the early stages of damage. The pitch drop experiment, in its upgraded post-2014 form, is essentially a structural health monitoring system for a glob of pitch. The webcam watches the geometry. The temperature sensors track the thermal environment. The whole setup is designed to catch the moment of failure, the pinch-off, and to understand the conditions that led to it. It's the same philosophy that governs how we monitor aging infrastructure around the world, just applied to a beaker on a shelf in Brisbane. And there's something poetic about that, if you think about it. The same principles that help us decide whether a 50-year-old bridge is safe to drive across, or whether a nuclear reactor's containment vessel is still sound, or whether the sealant on a spacecraft will hold for another mission. Those principles are playing out, in miniature, in slow motion, in a physics department display case. The pitch doesn't know it's being monitored. It doesn't know it's part of an experiment. It's just doing what it's always done, flowing, aging, responding to gravity and temperature and its own internal chemistry on its own inscrutable schedule. But there's one more twist to the story that I want to tell you about. One more connection that takes us somewhere unexpected. Because the pitch drop experiment isn't just about materials science and rheology and the patience of individual scientists. It's also become something else entirely. Something that Thomas Parnell could never have anticipated when he poured that heated pitch into a funnel in 1927. It's become a kind of philosophical object, a meditation on observation itself, on what it means to watch and wait, on the relationship between the observer and the thing observed. And the person who crystallized this idea, who turned the pitch drop experiment into a touchstone for thinking about patience and presence, wasn't a philosopher at all. It was John Mainstone, the very same physicist who spent decades watching and waiting and never once seeing a drop fall. Now, I know we talked about Mainstone earlier, about his long vigil, about the cruel near misses, away for a cup of tea during one drop, on holiday during another, the camera malfunctioning at exactly the wrong moment. But here's what I didn't tell you before. In the later years of his life, Mainstone started giving interviews and writing about the experiment in a way that went beyond physics. He began to articulate something that had been quietly growing inside him through all those decades of observation. He talked about the experiment as a lesson in humility, not just scientific humility, though there was that too, the recognition that nature operates on timescales that don't care about your schedule, your grant cycle, your career ambitions, but a deeper kind of humility. The humility of realizing that some things resist being witnessed on demand. Think about that for a second. We live in a world that is obsessed with capturing the moment. Every phone has a camera. Every event is live-streamed. We have satellites that photograph every square meter of the Earth's surface every few days. We have particle detectors that can register events lasting femtoseconds. That's a millionth of a billionth of a second. We are extraordinarily good at watching things. And yet, here was this lump of pitch in a glass funnel. doing something as mundane as dripping, and for over 80 years, no human being managed to see it happen. Not once. The drops fell when no one was looking, when the camera was broken, when the power was out, when the custodian of the experiment had stepped away for just a moment. It's almost as if the pitch had a sense of comic timing. Mainstone didn't quite put it that way, but he understood the absurdity, and he wore it lightly. In interviews, he'd laugh about it, but underneath the laughter, there was something genuine, a recognition that the experiment had taught him more about the nature of observation than any physics textbook ever could. Because observation isn't passive. It's not just pointing your eyes at something and waiting. Observation requires patience, yes, but it also requires a kind of faith. Faith that the thing you're watching will eventually do the thing you're waiting for, even though you have no guarantee. And it requires you to accept that you might miss it anyway. There's actually a beautiful parallel here to quantum mechanics, and I don't want to stretch the analogy too far, because the pitch drop experiment is entirely classical physics. There's nothing quantum about a glob of tar dripping from a funnel, but the philosophical resonance is real. In quantum mechanics, the act of observation changes the outcome. The famous thought experiment with Schrödinger's cat, the debates between Bohr and Einstein about whether the moon exists when nobody's looking. These are questions about the relationship between the observer and reality. The pitch drop experiment asks a much simpler version of the same question. Does the drop fall if nobody sees it? Well, yes, obviously it does. The pitch on the beaker floor proves that. But there's something unsettling about a phenomenon that, for the better part of a century, seemed to actively evade human witness. It makes you wonder what else is happening in the world right now, at this very moment, that nobody is watching. And this is where the experiment starts to connect to something broader in the philosophy of science. There's a concept called the problem of induction, which goes all the way back to David Hume in the 18th century. The basic idea is this: just because something has happened a certain way every time you've observed it, doesn't mean it will happen that way next time. The sun has risen every morning of your life, but that doesn't logically prove it will rise tomorrow. It just makes it very, very likely. Hume argued that our confidence in the regularity of nature is based on habit, not on logical necessity. We expect the future to resemble the past because it always has, but that expectation is itself based on past experience, which makes the reasoning circular. Now, the pitch drop experiment is a funny case study for the problem of induction. We know the pitch will drop again. We're confident of that. The physics is clear. Gravity is pulling on the pitch is flowing, and eventually the neck will thin to the point of pinch-off. But when? The intervals between drops have been getting longer. Remember, the early drops fell every 8 or 9 years, but the most recent ones have stretched to 12, 13, 14 years. Is that trend going to continue? Will the 10th drop take even longer? Will there be a point where the pitch has aged and cross-linked so much that it effectively stops flowing altogether and no more drops ever fall? That's a real question, and nobody knows the answer with certainty. The experiment is still running, still gathering data, still waiting. And every year that passes without a drop is both a data point and a deepening of the mystery. Here's the thing about long-duration experiments. They force you to confront the limits of prediction. In most of experimental science, you design an experiment, you run it, you get results, you publish, you move on. The whole cycle might take months or a few years, but when your experiment runs for a century, the world changes around it. The building gets air conditioning. the custodian retires or passes away. The institution's priorities shift. Funding comes and goes, and the material itself changes, aging in ways you didn't anticipate and maybe can't fully characterize. The experiment becomes entangled with history in a way that short experiments never are. And that entanglement is part of what makes the pitch drop experiment so fascinating as a philosophical object. It's not a controlled experiment in the way we usually think about controlled experiments. There's no control group. There's no way to reset and run it again from the beginning. Well, you could start a new one with fresh pitch, and in fact, people have done exactly that. But it wouldn't be the same experiment. It wouldn't have the same history, the same accumulated aging, the same decades of thermal cycling and oxidative exposure. The original experiment is unique. It's a one-of-a-kind artifact, as much a historical object as a scientific instrument. This is something that the people at the University of Queensland understand deeply. When they upgraded the monitoring equipment after the 9th drop in 2014, they were very careful not to disturb the experiment itself. The new sensors were placed around the funnel, not on it. The webcam was upgraded to higher resolution, but it still just watches from outside the glass case. Nobody has touched the pitch or the funnel or the beaker since Parnell set it up. The stand, the glassware, the pitch itself, it's all original. And that continuity matters. It's part of what makes the data meaningful. If you replaced the funnel or added fresh pitch, you'd lose the thread. You'd break the chain of observation that stretches back to 1927. There's a wonderful phrase that sometimes gets used in the context of long-running scientific projects: cathedral thinking. The idea is that some endeavors are so large, so long-term, that the people who start them know they won't live to see them finished, just like the medieval masons who laid the foundations of cathedrals that wouldn't be completed for generations. The pitch drop experiment isn't quite cathedral thinking in the intentional sense. Parnell probably expected it to be a simple demonstration, not a century-long odyssey. But it's become cathedral thinking by accident. Parnell started it, Mainstone inherited it, and devoted his career to it. After Mainstone's death in 2013, the custodianship passed to Andrew White, a physics professor at the University of Queensland who specializes in quantum optics, which is about as far from slow-dripping tar as you can get in physics, but who took on the responsibility with genuine reverence, and someday, White will pass it on to someone else. The experiment will outlast all of them. And this raises a question that I find genuinely moving, especially late at night when you're lying here thinking about it. What does it mean to commit to watching something that moves slower than a human life? What does it mean to pour your attention into a process that won't reach its conclusion while you're alive? There's something almost spiritual about it, even though the experiment itself is resolutely physical, just gravity and viscosity and chemistry playing out one molecule at a time. You know, there's a Japanese concept called mono no aware, which roughly translates to the bittersweet awareness of impermanence, the gentle sadness that comes from knowing that beautiful things don't last. The cherry blossoms are beautiful precisely because they fall. And I think the pitch drop experiment evokes something like the inverse of that feeling. Call it the awareness of permanence, or at least of extreme persistence. The pitch is beautiful, in its strange way, precisely because it endures, because it's still there, still flowing, still doing exactly what it was doing when Parnell was alive, when Mainstone was a young man, when the world was a completely different place. The pitch doesn't care about any of that. It just flows. And maybe that's the deepest lesson the experiment has to teach us. Not about viscosity or rheology or the glass transition, though it teaches us about all of those things. Maybe the deepest lesson is about time itself, about how our experience of time is radically different from the experience of time embedded in materials, in geology, in the slow processes that shape the physical world. We talked earlier about James Hutton standing at Siccar Point and grasping the vastness of geological time, and the pitch drop experiment is a tiny, domesticated version of that same revelation. It's deep time in a display case. It's a window into a pace of existence that we can measure but can never truly inhabit. The 10th drop, whenever it comes, will be the first one that's been properly watched from start to finish, from the moment the 9th drop separated to the moment the 10th drop falls. Every stage of the process will be documented. The slow bulging, the gradual thinning of the neck, the final pinch-off. For the first time in the experiment's history, we'll have a complete record of a single drop's life cycle, and that record will be invaluable for testing all those theoretical models we talked about. The plateau-Rayleigh instability, the viscoelastic pinch-off dynamics, the self-similar scaling near the moment of separation. The data will help refine our understanding of how extremely viscous fluids behave under sustained stress over very long timescales. But here's what I keep coming back to, what I find myself thinking about. When I imagine that 10th drop finally letting go and falling into the beaker. It's not just the physics that matters. It's the fact that someone will be watching. After nearly a century of missed moments, of broken cameras and empty rooms and cups of tea at exactly the wrong time, someone, probably thousands of someones, watching on the live stream from all over the world, will finally see it happen. And in that moment, the experiment will complete a circle that Thomas Parnell started drawing in 1927, a circle that encompasses not just the science of how pitch behaves, but the much larger question of what it means to pay attention to the world around us, to watch carefully, to wait patiently, and to trust that the universe will eventually show you what you've been waiting to see. But the pitch drop experiment isn't just a philosophical curiosity or a sentimental favorite of physics departments. It turns out that in the last couple of decades, it's become genuinely useful in ways that connect to some of the most pressing engineering challenges of our time. And to understand why, we need to talk about something that might seem unrelated at first: the problem of predicting how materials will behave not over years or decades, but over centuries and millennia. Because there's a class of engineering problems where getting that prediction wrong isn't just expensive, it's potentially catastrophic. And I mean that in the most literal, most consequential sense imaginable. Think about nuclear waste. Right now, in places like Finland, Sweden, the United States, and France, engineers are designing repositories meant to store spent nuclear fuel deep underground, and the timescales involved are almost incomprehensible. Some of the isotopes in high-level nuclear waste remain dangerously radioactive for tens of thousands of years. Plutonium-239 has a half-life of about 24,000 years. So when you're designing a containment system for that material, you're not designing for the next century. You're designing for a span of time longer than all of recorded human history. You need to predict how your containment materials, the copper canisters, the bentonite clay buffers, the concrete barriers, the surrounding bedrock, will behave over millennia. Will the copper corrode? Will the clay swell and seal properly? Will the concrete creep and crack? Will the bitumen, and yes, bitumen, pitch's close cousin, is actually used as a matrix material in some nuclear waste encapsulation processes. Will it flow, deform, or degrade in ways that compromise the seal? And here's where the pitch drop experiment stops being a charming curiosity and starts being genuinely important. Because one of the hardest problems in materials engineering is extrapolation. You can run an accelerated aging test in a lab, heat things up, increase the stress, speed up the chemistry, and try to predict what will happen over centuries from data gathered over months. But accelerated tests have limits, and we talked about those limits earlier. You can't always be sure that the mechanisms you're accelerating are the same ones that will dominate at lower temperatures over longer times. The Arrhenius equation gives you a framework, but it assumes the degradation mechanism doesn't change, and sometimes it does. Sometimes a material that degrades one way at high temperature degrades a completely different way at low temperature over long periods. You get a different answer depending on how you ask the question. So what do you really want? You want actual long-duration data. You want to know how a material genuinely behaves when it sits under its own weight at ambient temperature for decades. And the pitch drop experiment is one of the very few sources of that kind of data on the planet. Nearly 100 years of continuous observation of an extremely viscous material creeping under gravitational stress. That's not a toy experiment anymore. That's a calibration point for the models that engineers use to predict long-term material behavior in some of the most consequential infrastructure projects ever attempted. The Finnish repository, called Onkalo, is being carved into granite bedrock on the island of Olkiluoto. The name Onkalo means cave or hiding place in Finnish, and the facility is designed to be sealed permanently sometime around 2120 or so. The waste will be encapsulated in copper canisters surrounded by rings of compressed bentonite clay, and the whole assembly will be placed in vertical boreholes drilled into the tunnel floors, about 400 meters underground. The idea is that the bentonite will absorb groundwater and swell, creating a nearly impermeable barrier around each canister. But nearly impermeable has to mean something very specific when your timescale is 100,000 years. The bentonite will creep. The copper will corrode slowly. The rock itself will shift as ice ages come and go, because yes, they have to account for future glaciation. The weight of a kilometer-thick ice sheet pressing down on the Finnish bedrock will change the stress field around those tunnels. Everything moves. Everything flows. The question is always how fast. And that question, how fast does something that looks solid actually flow, is exactly the question that Thomas Parnell asked in 1927 when he poured heated pitch into a glass funnel and waited. He probably never imagined that his little demonstration would become relevant to nuclear waste storage. But that's how science works sometimes. The most important data comes from the most patient experiments, and you often don't know what you're going to need until you need it. There's another area where this kind of long-duration material behavior matters enormously, and it's one that connects back to something we talked about much earlier, the question of whether old glass flows. Remember, we established that window glass doesn't measurably flow on any human timescale. Its viscosity is so astronomically high, something like 10 to the 20th Pascal seconds at room temperature, that you'd need to wait longer than the age of the universe to see any detectable sagging. But there are glassy materials with lower viscosities, materials that sit in that fascinating middle zone between obvious solid and obvious liquid. And some of those materials are used in engineering applications where even tiny amounts of flow over decades could matter. Metallic glasses, for instance. These are alloys that have been cooled so rapidly that their atoms didn't have time to arrange themselves into a crystalline lattice. They froze in a disordered, amorphous state, like window glass but made of metal. And metallic glasses have some remarkable properties. They can be incredibly strong, resistant to corrosion, and they can be molded into very precise shapes. They're used in things like transformer cores, surgical instruments, and even some smartphone components. But they're not in thermodynamic equilibrium. They're slowly, imperceptibly relaxing toward a more stable state, and that relaxation can change their properties over time. They can become more brittle. Their dimensions can shift by tiny amounts. In precision applications, that matters. Understanding how amorphous materials age over very long periods, how their internal structure slowly rearranges, how their mechanical properties drift, is a problem that connects directly to the kind of data the pitch drop experiment generates. Pitch is, in a sense, a model system for studying the long-term behavior of disordered materials under stress. It's messy and complex, sure, with its polydisperse mix of aromatic hydrocarbons and its tangled networks of pi-pi stacking. But that complexity is actually a feature, not a bug, because real engineering materials are messy and complex too. The neat, idealized systems we study in textbooks are useful for building intuition, but the real world is full of materials that don't fit neatly into categories, materials that are a little bit solid and a little bit liquid, depending on how you look at them and how long you wait. And this brings us to something that I think is one of the most beautiful ideas to come out of the whole pitch drop story. And it's an idea that connects the physics to something much broader. It's the idea that time itself is a variable in how we understand the world, not just in the obvious sense that things change over time, but in the deeper sense that the timescale of your observation determines what you see. We talked about the Deborah number earlier, the ratio of a material's relaxation time to the time you spend observing it. When the Deborah number is high, things look solid. When it's low, things look fluid. But here's the thing, the Deborah number isn't just a property of the material. It's a property of the relationship between the material and the observer. Change the observer's time scale, and you change what the material appears to be. This is genuinely profound if you sit with it for a moment. It means that the categories we use to describe the physical world, solid, liquid, rigid, fluid, permanent, temporary, aren't absolute properties of things. They're descriptions of how things behave relative to the time scale on which we happen to be paying attention. Mountains are solid on the time scale of a human life. On the time scale of geology, they flow like waves. Glass is rigid on any time scale you or I will ever experience. But on a time scale of billions of years? Maybe not. The pitch in that funnel in Brisbane is a solid if you poke it with a hammer. It's a liquid if you watch it for a decade. It's both. It's neither. It's pitch. And I think that's why the experiment has captured people's imaginations so thoroughly, beyond the quirky charm of it, beyond the human drama of John Mainstone spending his career watching and waiting. It's because it makes visible something that's usually invisible, the fluidity of categories, the way that patience can reveal truths that urgency misses. In a world that increasingly values speed, instant results, real-time data, the pitch drop experiment is a quiet argument for slowness, for watching, for letting things take the time they take. Andrew White, who inherited the custodianship of the experiment, has talked about this. He's a quantum physicist by training, someone whose day job involves phenomena that happen on timescales of femtoseconds and nanoseconds, unimaginably fast events in the subatomic world. And yet, he's also the custodian of one of the slowest experiments ever conducted. He said that there's something grounding about it, something that puts his other work in perspective. The universe operates on every timescale simultaneously, from the quantum flicker of a virtual particle to the billion-year creep of a continental plate. The pitch drop experiment just happens to sit in a sweet spot where the timescale is long enough to feel geological, but short enough that a human life can encompass several drops. It's a bridge between human time and deep time, and standing on that bridge, you can look in both directions. The experiment will keep running. The 10th drop will fall, maybe in the 2020s, maybe in the 2030s, depending on temperature and the continued slow aging of the pitch. And when it does, it will be the most thoroughly documented drop in the experiment's history. Every instrument will be watching. The rheological models will be tested against real data. The pinch-off dynamics will be captured in detail that would have been unimaginable to Parnell, or even to Mainstone for most of his career. And then the 11th drop will begin to form, slowly, imperceptibly, and someone will keep watching. There's something I want to leave you with, and it's not really about pitch at all. It's about the kind of knowledge that only comes from sustained attention. We live in an era of extraordinary scientific capability. We can smash particles together at nearly the speed of light. We can image individual atoms. We can sequence an entire human genome in a day. But some things can only be learned by waiting. Some truths only reveal themselves to those who are willing to sit with a question for years, for decades, for a lifetime. Thomas Parnell understood that when he set up his funnel and his beaker in 1927. John Mainstone understood it when he committed his career to watching. And in a way, every engineer who designed something meant to last, a bridge, a dam, a repository for nuclear waste, a cathedral, is making the same bet. They're betting that they understand how materials behave not just now, but far into the future. They're betting on patience, on careful observation, on the slow accumulation of knowledge over time. The pitch is still flowing tonight, right now, in that climate-controlled room in Brisbane. It's been flowing since before the Second World War, since before the transistor was invented, since before anyone had heard of DNA. It flowed through the moon landing and the fall of the Berlin Wall and the invention of the Internet. It doesn't care about any of that. It just flows. Molecule by molecule, those tangled aromatic hydrocarbons sliding past each other in their slow, stately dance, driven by nothing more than gravity and their own weight. A few billionths of a meter per hour. Invisible to the eye. Undeniable over decades. And if you're still awake, though it's perfectly fine if you're not, if you've already drifted off somewhere between the nuclear waste and the metallic glasses, I want you to imagine that funnel for a moment. Picture it in the quiet of the lab, late at night, when no one is there except the cameras. The building is still. The air is cool and steady. And the pitch is doing what it has always done. What it will keep doing long after you and I have stopped thinking about it. It's taking its time. It's not in any hurry. It's just letting gravity do its patient, invisible work, one molecule at a time, 1 hour at a time, 1 year at a time. And there's something deeply restful about that, I think. The idea that not everything has to happen quickly, that some of the most important things in the world happen so slowly that you can't even see them happening, that patience isn't just a virtue, it's a way of understanding the universe, and that sometimes the most profound thing you can do is simply watch and wait and trust that in its own time, the drop will fall.